Fused deposition modeling, or FDM, is a layer additive manufacturing process that uses production-grade thermoplastic materials to produce both prototype and end-use parts. This technology is known to accurately produce feature details and has an excellent strength-to-weight ratio. FDM is ideal for concept models, functional prototypes, manufacturing aids, and low-volume end-use parts. The FDM process begins by slicing 3D CAD data into layers. The data is then transferred to a machine, which constructs the part layer by layer upon a build platform. Thin thread-like spools of thermoplastic and support material are used to create each cross-section of the part. Similar to a hot melt glue gun, uncoiled material is slowly extruded through dual heated nozzles. The extrusion nozzles precisely lay down both support and thermoplastic material upon the preceding layers. The extrusion nozzle continues to move in a horizontal XY plane while the build platform moves down, building the part layer by layer. The finished part is removed from the build platform and cleaned of its support material. Raw FDM parts have visible layer lines. However, service providers such as Solid Concepts offer multiple finishing options to create smooth, even surface parts including hand sanding, assembly, and cosmetic paint. Since FDM parts are constructed with production-grade thermoplastics, including ABS, polycarbonate, and Ultem, they are both functional and durable. FDM is utilized in a number of industries, including aerospace, automotive, industrial, commercial, and medical.
Laser sintering, or DMLS, is used to produce metal parts ranging from prototypes to production tools. The DMLS process builds using STL files that are extracted from 3D CAD models. A technician works with this 3D model to properly orient the geometry for part building, adding support structures where necessary. Once this build file has been completed, it is sliced into layers and loaded into the machine software. Inside the chamber are a build and material dispensing platform along with a recoater blade used to move new powder over the build plate. The technology fuses each layer of metal powder into a solid part by melting it locally using a 200-watt fiber optic laser. Parts are built up additively using 20 or 40 micron layers. A combination of both solid and support materials are used to maintain geometric integrity. Fully dense parts are grown in a variety of metals, including tool steel, stainless steel, cobalt chrome, and bronze alloy. Parts straight off DMLS machines have a fine investment cast finish. These metal materials can be polished or benched to your discretion, capable of meeting the needs of any project. Unique geometric freedom of design enables DMLS to form cavities and undercuts which, with conventional methods, can only be produced with great difficulty. DMLS is ideal for demanding design applications, including conformal cooling channels within tools and tooling inserts, as well as customized medical implants. DMLS makes it possible to design internal features and passages that cannot be cast or machined. Complex geometries with multiple components can be simplified, eliminating the need for assembly. The lead time for receiving a traditionally tooled part can take weeks, creating a large bottleneck in the production process. DMLS produces parts in a matter of hours or days. The parts have excellent mechanical properties, high detail resolution, and exceptional surface quality. DMLS parts can undergo functional testing in the environment for which they were designed. Since DMLS uses most alloys, prototypes can be made out of the same material as production components. The ability to generate functional metal prototypes in short order radically impacts design processes, accelerating design cycles with time to market. The advantages do not stop with prototyping. DMLS is one of the few direct digital manufacturing technologies used in production, increasing design efficiency for technical applications. DMLS technology delivers unlimited potential for engineers to create previously impossible solutions, embracing a new era of design-driven manufacturing.
Selective laser sintering, or SLS, is a rapid prototyping technology that turns 3D CAD data into physical parts in a matter of hours. SLS is an additive manufacturing technology that uses powdered nylon 11, nylon 12, and PEEK materials. Parts produced are lightweight, highly durable, and both heat and chemical resistant, making SLS an excellent choice for producing production parts without the expense of tooling. The SLS process begins by splitting 3D CAD data into thin cross-sections or layers. The data is then transferred to the SLS additive manufacturing equipment. The machine then begins to create the first layer. After a leveling roller spreads a thin layer of powdered material across the powder bed, a CO2 laser traces the cross-section on the material. As the laser scans the surface, material is heated and fused together. Once a single layer is complete, the powder bed is lowered to make room for the next layer. More material is introduced from the powder cartridge and rolled out smooth, while unused material is recycled. The process is repeated, building layer upon layer until the part is complete. As SLS parts are built, they are encompassed by unsintered powder, which provides supplemental strength and eliminates the need for support structures. Complex designs and assemblies, once thought impossible, are now being redesigned with SLS as cost-effective integrated structures. Solid Concepts manufactures parts utilizing nylon with property-enhancing fillers to create rugged SLS parts suitable for a variety of prototype and production applications. Typical uses for SLS include tools and fixtures, fuel tanks, flight-rated components for unmanned aerial vehicles, automotive designs, air ducts, architectural models, and artistic sculptures. PolyJet is a layer additive manufacturing technology used to develop plastic prototypes from 3D CAD data. This rapid prototyping process uses inkjet technology combined with UV curable materials to quickly and economically produce highly detailed and accurate physical prototypes. PolyJet is one of the fastest prototyping processes available to develop high-precision physical parts and is ideal for smaller parts, appearance models, and master patterns. The PolyJet process begins by slicing CAD data into cross-sections or layers as thin as 6/10,000ths of an inch. The data is then transferred to the PolyJet machine, which begins constructing the object one layer at a time. Similar to how an inkjet printer lays down pigment, the PolyJet printhead deposits small amounts of ultraviolet curable material on the build platform, eventually forming a single cross-section of the part. An ultraviolet light attached to the printhead simultaneously cures the material as it is printed. Once a cross-section is complete, the build platform is lowered slightly to make room for the next layer. As the part is built, support material is added to give supplemental strength to fine structures and down-facing surfaces. After all of the layers have been created, the finished part is removed from the platform and cleaned. Although finishing is not necessary, a number of hand sanding and paint options are available through service providers such as Solid Concepts. PolyJet parts are well suited for quick, economical prototypes requiring exceptional detail, surface finish, and edge visualization. PolyJet is ideal for a wide range of industries, including medical, entertainment, consumer products, automotive, and industrial design.